Alright, let's talk about a state space model for our temperature control lab. State space models, I've seen some people be intimidated by them. It's really just a form that we get our equations in so that we're able to utilize everything in a much easier way. The way that's going to look here, I'll just use my pen on the computer real quick, is we have x, which is something that it's a rate of change. It's our rate of change of our variables, and that's going to be equal to ax plus bu, and then I'll write the other ones down real quick. The other equation is y is equal to cx plus du. So let's talk about what each of these variables mean really quickly. You'll note that this right here, this x and this x they're both x. X dot is another way of saying that we have a derivative of something. So it's the rate of change of something with respect to itself. And u. U is going to be our inputs. And these are going to be our states. So we have our inputs and our states and how they relate to one another. And then we have this other equation, which is, again, this time it's not the full, it's not the derivative of themselves, I should say. Here we have the derivatives in with respect to themselves. It's another way of us having our equation for what the states actually are equal to at different times. So it's an equality versus here we have the derivatives and what the derivatives may be, and here we just have what the states are and equations that are dependent on the states themselves. Let's go ahead, let's get rid of this, and let's talk about our system. We're going to derive these matrices from first principles equations. So the first thing we'll do is we'll regress our temperature control lab parameters. So if we don't have this this file step response, we're going to go ahead and do a step response and regress the files. So we go through a similar thing we've done a long time now. We do a step response, 10 minutes, and grab the data. Then we save it. We've got our time, temperature 1, temperature 2, Q1, Q2. Nothing fancy there. Just looking here. I don't see a time for it to stop, so let's go ahead and do that again. And say pause for 1 minus mod talk and 1. So that should set us to pause. Just notice that there wasn't anything to pause, so now we have something to pause there. Finally, we close lab off, clear lab, so that we don't have any problems with it. We've done this before a number of times. Excuse me. Just a number of times, we're going to regress the parameters for our system. So we're going to regress U, which is the heat transfer coefficient with the surroundings, US, which is the heat transfer coefficient between the two heaters, alpha 1, alpha 2, that's the relationship between the percentage power and the actual heat going into the system, and then tau, the process time constant. So we have these 5 parameters. We have our initial guesses right here of 10, 20, 0.01, 0.05, 0.005, I should say, and 10. I can tell you right now that's going to be too small. And then the way we do this with we're going to do fmincon, which is our constrained minimization, or our constrained optimization, where we're going to minimize our objective function. And we're going to do that is using this relationship, these inequality constraints. The ax is less than or equal to b. So for our lower bounds, we're going to do -1. So -1 of our u is going to be less than or equal to 1. And so if you multiply the negative over, u is greater than or equal to 1. And so that's how we get our lower bounds. Our upper bounds, similarly, 1 times u is less than or equal to 20. So we're between 1 and 20. Similarly, for our US, we're between 5 and 40. And that's how these bounds go. We go ahead and we create our objective function down at the very bottom of this, this exercise. And the way we do that is we take our model like we've done before, we unpack the states since those are integrated at every time step. We unpack the regressed constants as well. And then we have these other constants, which we're not regressing, we're taking to be known. And then we simulate the temperature change for our second order. This is a second order. We have derivatives of T1 and the heaters and the sensors, which depend on the heaters. So we have a second order system. We return the derivatives. Then we have a function to simulate that model. We've done this before. And then our objective function compares our simulated model's data to the measured data. And then we try to minimize the sum squared error between the two. So let's come back up to our regression right here. So we'll display our solution, and then we'll go ahead and unpack it and view those parameters, and then assign them to variables so that we can use them later. Finally, we're going to graph it just so we can see how everything looks. So we'll go ahead and do that. I'll just run this section right now. And we're coming up with an error. Let's come up here, see if everything worked well up here. It did not. So I'm going to go ahead, down here we're going to fill these in together. I'm just going to go ahead and hit zeros for now for all these, just so we can get it to run. I thought as it should run, we should check that there's a section break, but it looks like there is. This looks like a section break to me if I've seen one. Insert, live editor, section break. Yeah, we have a section break. So go ahead and run the section now. It just saw some easy syntax errors, so it took care of it. We have our A read from the matrix just fine. Here's the end of our fmin_con. Actually, that's the answer is equal to fmin_con. Oh, we did. That was our initial objective function. That's what that was. So let's see what our ending. Oh, here we're going. So let's go ahead. Let's just look at our parameters first. Q2 doesn't change much. Our solution is going to be 440. That seems high, and that is the upper bound, which tells us that something didn't go quite right. And then 32 for tau. Seems decent. The fact that alpha 1 and alpha 2 are the same also, don't really love that. So we're going to go ahead and do this. Maybe I don't like our data. So we're going to go ahead. We're just going to hit delete this. Yes. We're going to go ahead and do this again. And I'll go ahead and pause it. We'll see once it's all simulated. All right, we've got a much better shaped graph now. I like seeing some movement. So let's regress our stuff again. Our constants, I should say. Let's be specific. Again, we have some error. That's obviously going to be more because we have more data. It's going to take some time, really think about this, and that's all right. We wanted to think long and hard. Come up with a good solution. While it's thinking, let's go ahead and just... Oh, I got done thinking. All right, so our U... Oh, it's already going, even more. U regressed is about 4. US is about 11. I like the difference. There's obviously more heat transfer between the two heaters than just the surroundings in general. Alpha 1 is just a little bit less than 0.001. Alpha 2 is about 0.005. I like that. That's well within the range we like to see. And our tau is 32. Again, within that range, we're not at any of the limits, which kind of tells us that we did succeed in finding a solution. And now we can see how well our graph worked. Obviously, we have the wrong starting temperature. This started a little bit high. But that still looks pretty good, and we still reflect the dynamics pretty well, so we're going to live with it. We like that. Let's go ahead now and let's discuss our state space model. We have here the state space model right here as far as the x dot and the in terms of itself, x. So the change in x in terms of a times itself plus b times the inputs. And we also have y is equal to c times x plus du. So where do we come up with these constants to fill in these matrices? You'll see we're going to be tackling that. Where to come up with those constants? Well, we have our physics-based models right here. So we've worked with this before. And if we define let's define our x, and that will make things make sense real quick. go ahead and get out the pen. X is going to be equal to TH1, TH2, TC1, and TC2. And while we're at it, let's define U. Our U is going to be Q1, Q2. So our A is going to we're going to have to be able to multiply our A. So we need 4 rows, 4 columns. Our U is going to have 2. So let's look at this. We see that 2 columns right there. So for example, let's look at our first row right here. The change with respect to heater 1. So the change, let's just go like this. I want to see everything. Let's maybe zoom out just a little bit. It's not super ideal, but it's not bad. Okay, let's think about this. Change in temperature 1 with respect to time. Well, we can see that pretty easily right here. So we're going to find an equation for our first equation justly. So what we'll do is we'll take that m times Cp, and we'll move it over here. And so then we just have it in terms of the other variables, or the other states, so the temperatures of these other things, and then plus the heater value of heater 1 and the heater value of heater 2 and what those are related to. So those portions will come in these Q's, especially, but we'll get there. So let's go ahead. We have our equation for heater 1 here. We have our equation for heater 2 here. We have the 2 temperature sensors, which depend on tau, this process time constant, and the difference between heater 1 and the sensor itself. So it's another thing where it depends on itself recursively. Finally, we have some relations to make things simple. The first is that QC12, so that the relationship between the convection energy transferred between 1 and 2 is equal to US times AS. And so it's just helping us have something to represent what's going on. That way we have fewer variables floating around. Same thing with R, QR12. That's the radiative heat transfer between the two. And finally our tau. Our tau is simplifying this relationship between the mass, the heat capacity, mass of the sensor, I should note, heat capacity of the sensor, and the difference in spatial relationship between the heater and the sensor itself, and divided by KAC. So let's go ahead. We're going to go ahead and actually we already have these filled in for A1. Here's our differential form. Derivative of the function with respect to H1, temperature of H1, at some T is equal to, so let's come up here just so hopefully we can see this, derivative of the function with respect to TH1 is going to be our A1 relationship. So the function here is going to be this F1, which is our H1 justly. So derivative of our temperature with respect to H1, just kind of thinking through what's going on, is going to be equal to negative UA plus 4 times epsilon sigma A to the T to the third, T naught to the third, plus US AS plus 4 epsilon sigma AS T to the T naught to the third again, divided by mass, divided by heat capacity. Well, let's just think about that just for a moment, because things will make it a little bit easier, and then we'll kind of cruise through. We'll get out the pen again and switch it to a pen. If we think about our balance that was going on before, let's actually, before we get out the pen, let's just scroll up. Let's talk about this balance right here. All right, now we're going to switch the pen one more time. All right, so we're taking the derivative of TH1. This is TH1 dt. So we have UA, all this right here, but we have this T infinity, that's also a T1, it's the ambient temperature, minus TH1, plus, so let's think about the derivative right here with respect to temperature 1. What's going to be negative, this quantity, derivative of it with respect to itself is going to be negative 1. because of that. Same thing here. Derivative of this with respect to itself is going to be 4 times 3t to the third. We're taking the derivative with respect to itself. This is a constant, it's going to go away. This is a constant, going to go away. So we're left with 4 times t to the third. I don't know why there was a 3 there. That was my bad. Times epsilon sigma alpha times the area. Same thing here. UA TH1 right here. But we also have a TH1 within this QC1 right here. So that's where we have the negative, again, that's going to go to 1, negative US AS. And this is going to go to just, it's a constant, so that's going to go to 0. So we just have the negative AS US. Then these two are not dependent on TH1. So at the end of the day, we have UA, negative UA, I'll just write them over here, negative UA is over MCP is one term. We also have negative 4t to the third epsilon sigma area over MCP. We have our, let's look at our QC1, QC2. Oh yeah, my bad. We do have a TH1 right here too. So first our QC12 is going to have, it's going to be a negative AS US over MCP again. You can see a pattern with this M divided by MCP. And then finally we have our QR12, which is going to be similar to up here. It's going to be negative 3t to the third. This is going to be a 4, not a 3. And then that times epsilon sigma AS. 1, 2, 3, 4 terms. Finally, we have our alpha Q1, but that's not dependent on our T1. So the derivative of this with respect to TH1, we get this over, and we take the derivative with respect to TH1. And then that's where we have these 4 constants. So let's go ahead and look at our code. We're given the first 2 as examples, these 2 that are up in the code. So let's see how we did it. The first thing that you'll notice is we had some of those normal-ish chunks already given to us. So for example, this chunk right here, the U times A, is our C1. This 4 times epsilon times sigma times A T naught to the third is equal to our C2. And you notice it's just T naught because we're using linearization here. Our USAS is going to be C3. The C4 is going to be this part that was the radiative heat transfer between the 2 heaters. And finally, divided by M times CP is going to be our C5. You'll notice there were negatives for all of these. We pulled that negative out front. And so if we look at our code for A1, we have negative C1 plus C2 plus C3 plus C4 divided by C5. Looking pretty snazzy. All right, let's look at A2 now. Well, remember, this is going to be the derivative with respect to A12. Let's come up here. Look at our, I always have to imagine this vector coming over and on top. It's going to be the change in H1 with respect to H2 now. So let's look at our physics-based equations. Don't see an H2 here. So let's look at what these 3 represent. QC12 has an H2. QR12 has an H2. And then alpha 1 Q1 does not. So we're going to get these 2 in terms of H2. So as we do that, derivative of this with respect to H2 is USAS, and it's also 4 times epsilon sigma AS TH2 at time 0 to the third. If we're taking the, again, we're taking the derivative. Let me back up a little bit. We're taking the derivative. We're using the fact that a Taylor series, some f of x, is approximately equal to f of x0 plus the derivative, so df, dx at x equals 0 times that delta x. So that's what we're doing. We're taking the derivative with respect to that x. Here, that's with respect to h2. And we're just using that as our approximation of the function, using this as well. So let's go ahead, because we're going for the derivative here in this portion. So that's how we can just take that derivative at x0. So let's go ahead, look at our A12. It was C3 plus C4. If you remember C3, that's AS, right here, C3 USAS. And then C4 is that 4 times that linearization. And of course, all divided by the mass times heat capacity, since that's at the bottom. There we go. That's how we derived that. So does T1 depend on C12 or TC1 or TC2? Well, let's look at these equations. Derivative with respect to this, it's nowhere there in the derivative, so we're good. The only thing we have left now is the U portion of the matrix, this portion right here. So how does T1, how is that affected by Q1? Well, it's just multiplied by alpha. So Q1 multiplied by alpha. So our B11, let's find that right now while it's on our minds. Our B11 is going to be alpha, but it's also going to be, again, divided by this MCP. So our B11, we have our alpha? No, we don't. So we're just going to have to go ahead and use, let me just make sure I have my variables right. Alpha 1, that's what it's called, divided by C5. So this isn't that bad. We're just looking at the physics-based equations, looking at linearization of it. And that's all the state space form is. It's a simple way where it's really easy for computers to do math with these matrices. And so we're able to do a lot of operations more efficiently, especially model predictive control, where we look at horizons. We look at how the effect of whatever change we're doing would affect across not just the next second, but like over whatever horizon we're interested in. And we're able to do that. So let's go ahead, let's think about TH2 and how that would be with respect to all of these variables. Now I'll give you a hint. As far as these right here, are there many differences between these two equations? Not many. In fact, the constants are the same, you could say, especially if H1 and H2 are at the same initial temperatures. The only difference here is that we have these negative signs. So let's think through what that means. Our UAs and these sigmas are going to be the same. So let's go ahead. We use these C's right here for those. So let's go ahead. We're just going to go like this. Row 2, column 1, we're going to have, let's just think this through. That's going to be in terms of H1. So where we had H2 is going to be what H1's effect will be on the system. And so they're going to be equal. It's going to be C3 plus C4 divided by C5. Similarly, what's T2's effect on itself? Well, it's going to be exactly the same as C1's effect on itself. Sorry, not C1, T1. The temperature of heater 1 will affect itself in the similar way that the temperature of heater 2 will affect its derivative of itself. And so we'll do this kind of in a fun way that we can do when we're doing code, and we can just say this is equal to A11. A little shortcut there for you. A31 and A33 are the next two that we still have values to find. So let's think A31 and A33. That's the temperature of the sensor with respect to H1 and with respect to itself. So let's think about this. Our temperatures for right here. Temperature of the sensor, derivative of that, with respect to H1 and itself. So it's going to be TH1 divided by tau, and it's going to be negative the temperature of itself divided by tau. So it's going to be 1 over tau. We have a variable for that. That's C6. So that's going to be positive C6 and negative C6. Now let's use how these systems are similar. Our A42 and our A44 are going to be the temperatures of the second sensor. So it's going to be exactly the same, and let's just, for fun, say that is equal to A31 and A33. The constants are, and I should be clear, this doesn't mean that the temperature sensor 2 is dependent on sensor 1, but it means the constants are the same, the derivative constants are the same, because they're similar systems. Finally, we have C13 and we have B22. Forgot about that one. B22 is going to this one right here. It's how heater number 2 affects the temperature of H2. Well, that's just alpha 2. We can do that easy. Alpha 2 divided by mass and divided by heat capacity. Or at C5. Finally, C13 and C24. Let's think through what these are representing here. Let's come up here, and there we have it. Oh, that makes it easy, doesn't it? This is our C right here, and this is our D. And the temperature the temperature of C1 is equal to temperature of C1. Not bad. Temperature of C2 is equal to temperature of C2. That's why we have these ones on the main diagonal. But since we don't have all four, we just have these two. And that's just so these two matrices can be added right after the multiplication. So that's going to be a 1 and a 1. Now what we do here is we make a matrix here. The zeros with a 4 is going to make a 4 by 4 matrix. And then we add in the values that we've identified. All the other ones are going to be 0. Same for B, C, and D. And then we'll perform the same step test using this sys function. Let's do a step test. Here's the U inputs. Here's the ambient temperature. And then here's our X0, which is our initial temperatures for T1, the heater temperature 1, heater temperature 2, and then sensor 1, sensor 2. We have our lens space, which we define here, which is, again, we're going from 0 to max time. And we're doing 601 spots. That's so we can line up with the temperature control lab sim 1. And we do this LSIM, which performs our our state space simulation. Finally, we go ahead and we plot it. So let's go ahead, we'll run this section now. And what do you know? We need our control system toolbox. Or we need our model predictive control toolbox. We also need our signal processing toolbox. One of these toolboxes. I'll probably do the control system toolbox and model predictive control toolbox, as we'll use that later. So I'll go ahead and download these. Alright, I apologize. I actually don't have a license to get these toolboxes, which is unfortunate, but when I made this I did. And so then we will be able to plot. Here is the plotted simulated state space model of the temperature control lab data. You'll know notice that we take the T1 and T2 from the measured data and we add them. Remember, in this state space model, we're looking at the deviation variables. We've done that for a bit now, and I've just referred to them shorthanded by the actual variable itself. We're looking at the change in variable. And that's also how we get these derivatives. The derivative of a change in a variable will be is where we get these kind of relationships, like this right here, where it's the infinite minus TH1. That's the initial conditions, if you will. And so that's why we got those T0s. I should have offhandedly explained that a little bit more. Then you should get a graph, and it should all work out well. Go ahead and leave a comment if there's a problem. I'm sorry I'm not able to show that final graph.